Hi and good day everyone. We are students from Network Analysis subject here to present on the application of Fourier transform in medical. We have selected magnetic resonance imaging MRI. We are 5 of us in the group and I am Puvindraj K. Subramaniam.
I am Muhammad Amir Akmal bin Yaakob.
I am Nur Farah Ilmi Razman.
I am Fatira Najha binti Burhanuddin.
And I am Nur Muhammad Amirul bin Azizi.
We have touched on several parts and the first one is the application of Fourier transform in electrical engineering. It is used in the electronic to test equipment mainly to check the frequency response of the circuit. It indicates the time domain to the frequency domain and transform continuous and discrete signals. For that, it is a tool to diagnose the circuit on their analysis, electronic and signal processing. A waveform will be made such as the sine wave, complex wave, triangular wave and square wave. It generalizes the phasor technique to a non-periodic function. For that, the method of doing so is applying it to a circuit with non-sinusoidal excitation and as the same method as a phasor technique. Basically, it's an Ohm law using the inverse Fourier transform to get the response in time. Moving on to the next. This is the example of calculation and we are asked to find out the V output using Fourier transform. First, convert T domain into omega domain by using or referring to the Fourier transform table. Reconstruct the circuit with the new values of V in, inductor and capacitor. Next, apply any of the circuit analysis and in this case, we have used voltage divider rule. Substitute the value of R and L to obtain transform function which is HW. The transform function times with V input to obtain the V output value. Then use partial fraction. To obtain the value of A, assume j omega is equal to -3. To find out B, assume j omega is equal to -2. Substitute the values and get the answers for A and B. Finally, apply inverse Fourier transform. Simplify the equation, use the Fourier transform table to obtain the answer.
Alright, I will explain to you about the introduction of our project. Alright, the Fourier transform is a linear transform that provides information about the frequency spectrum of the signal. The Fourier transformation Fw of a function of time Ft is given by using formula provided. You can use formula provided in the slide. Is it used in image processing for image enhancement, restoration, filtering and feature extraction to help image interpretation and characterization? It decomposes a function of time signal into the frequencies that make it up. Is it also used in image reconstruction methods for medical imaging system? For example, the Fourier transform is used for image reconstruction in MRI. I will pass to Amir.
Thank you, Fatin. And I will explain the application of the Fourier transform in medical field. Our group decided to choose MRI machine as one of the example of devices that applying Fourier transform. Magnetic resource image is a scanning technique for creating images of human body without radiation. Next. How MRI works. First, the magnetic field is used to align hydrogen protons in the body. Second, radio frequency waves are absorbed by the protons and emitted as signal. Third, a radio frequency coil picks up the signal and transmits it to the computer. And the last step is the computer process the data and an image is generated. Next, this is the end of the MRI process, which is we will applying inverse transform. Inverse Fourier transform is one of the standard method reconstructing magnetic resonance imaging from uniformly sample case-based data. Next slide will be presented by Amirul.
Okay, thank you, Amir. My name is Amirul and I'll be representing about how does the MRI scan work. When you lie under the powerful scalar magnets, the protons in your body line up in the same direction, in the same way that a magnet can pull the needle of a compass. Short bursts of the radio waves are then sent to the certain areas of the body, knocking the protons out of the alignment. When the radio waves are turned off, the protons realign. This sends out radio signals which are picked up by the receiver. These signals provide information about the exact location of the proton in the body. They also help to distinguish between the various types of tissue in the body because the proton in different types of tissue realign at a different speed and produce distinct signals. In the same way that millions of pixels on the computer screen can create complex pictures, the signals from the millions of protons in the body are combined to create a detailed image of the inside of the body.
For the calculation, first of all, simple sine wave. Okay, the frequency is 1/2 pi. The period is 2 pi. Substitute the frequency and period into the equation given and obtain the answer. Next, a complicated sine wave. We can add the simpler wave shown in figure 1, figure 2 and figure 3 to obtain the complicated wave. Next, Fourier transform of the GT. Okay, it can be rewrite as infinite sum of simple cosine and sine wave by progressively increasing their fundamental frequency by integers and by varying their amplitude AN and BN. But assume substitute GT is equals to 1 and obtain the answer. Next, the Fourier series for square wave. Okay, it is given by y is equals to 1, 0 lower than x lower than pi, 0 lower than x more than pi, can be approximated with increasing accuracy by addition of simple sine and cosine wave of progressively increasing frequency. Next, Fourier series for a square wave. Okay, substitute n is equals to 1, 3 or 9 into the equation given to obtain the answer. Next, substitute n is equals to 51 into the equation to obtain the answer. Fourier transform and inverse Fourier transform. Fourier transform of a complicated signal GT which exists in time or spatial domain gives an expression for frequency domain which is GF. When plotted, frequency domain displays individual frequency and related amplitudes of simpler waves constituting GT. The inverse Fourier transform IFT of GF restores the time domain. Next, I would like to call upon Adlin.
Thank you, Bovin. Result and discussion. In this discussion, I will explain the process of Fourier transform in MRI system. The first one is Fourier transformation. Fourier transformation is the mathematical procedure connecting to time domain and frequency domain. Next. As we can see the figure, the process of time domain to frequency domain is Fourier transform, and from frequency domain to time domain is inversely Fourier transform. Next. Second process is spatial frequency. Spatial frequency is image can be decomposed into a set of planar waves varying in pace, frequency, amplitude, and direction. It is also the number of wave cycle, which is line pair per unit distance. As we can see the figure, the time domain becomes space domain and frequency domain is called spatial frequency. Next. The result is if the long image distance is become low spatial frequency and if short image distance is become high spatial frequency. Next. The third process is 2D Fourier transform and MRI image reconstruction. In this process is to decompose a 2D image. So the first step, as we can see, the original image is decomposed row by row, become gray level of line is chosen. After that, next, this is spectrum obtained. From this spectrum, the image is low spatial frequency. Next. The second step of 2D Fourier transform is second 1D Fourier transform in orthogonal direction, which is column by column. Next. This is final result is called Fourier plane that can be represented by an image. Next. The fourth process is K-space. K-space is array of number representing spatial frequency in the MR image. The readout MR signal is stored in K-space, which is equivalent to a Fourier plane. Next. Next process is gradient and spatial frequency. This process is cause how different in the spatial and contrast of the result MRI image. If the low amplitude or short duration gradient was encoded low spatial frequency, and if high amplitude is or long duration is become high spatial frequency. Next, so as we can see the figure, in the first figure at the center of case space is have low spatial frequency, and if at periphery of case space he have high spatial frequency. Next, the last process is linear trajectory through case space. This is an easier way to fill the case space. Use a line-by-line linear trajectory. The result image is contained at the beginning the each information with the low contrast. Then the general shape and contrast with a blur in the vertical direction disappear as high vertical spatial frequency information are complete. Next, I will pass to Fatin to give the conclusion.
Alright, thank you, Adrian. Okay, so we can conclude that the Fourier transform is widely used for designing filters. You can design system will reject high frequency noise and just retain the low frequency. It's natural to describe in the frequency domain. In medical science, image processing has enabled for accurate and fast quantitative analysis and visualization of medical image of numerous modalities such as MRI, CT scan, and also X-ray. It has also enabled doctors and researchers at remote sites to easily share data and analyze, thereby enhancing their ability to diagnose, monitor, and treat various medical disorders. Alright, I will pass to Puvin.
Actually, these are the resources that we obtain the informations such as journal papers, books, and also from internet. So we hope that this presentation will be useful in future. So that's all from us. Thank you very much.